Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with Titan's methane lakes, sailing through a world of liquid gas. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. Titan, Saturn's largest moon, presents a landscape unlike any other in the solar system. Its thick atmosphere, primarily composed of nitrogen, shrouds its surface in a perpetual haze, obscuring details from direct observation. This region is marked by an array of intriguing features, including vast lakes and rivers made primarily of liquid methane and ethane. These hydrocarbons remain in a fluid state due to Titan's frigid temperatures, which hover around -298 degrees Fahrenheit. The surface of Titan is a complex interplay of geological processes, shaped by both erosion and sedimentation. The presence of liquid bodies suggests a hydrological cycle that mirrors aspects of Earth's water cycle, albeit with different materials and conditions. It is this cycle that contributes to the Moon's unique weather patterns, including cloud formation and precipitation. Beneath its dense atmosphere lies a diverse terrain, where regions of solid ice contrast with sprawling liquid expanses. Radar and infrared observations have revealed the Moon's intricate topography, including smooth plains, rugged mountains, and extensive dune fields. These features hint at a geologically active world, where processes such as cryovolcanism may play a role in shaping the landscape. Titan's enigmatic environment continues to captivate scientists, inviting further exploration and study into its rich and varied characteristics. This dense haze envelops Titan, creating a unique atmospheric layer that distinguishes it from other celestial bodies. Composed primarily of nitrogen, this atmosphere is thick and complex, with a surface pressure approximately 1.5 times that of Earth. The presence of methane plays a critical role, contributing to both the atmospheric chemistry and the formation of clouds. These clouds produce methane rain, which nourishes the expansive lakes and rivers below. The haze's rich organic chemistry gives rise to a variety of photochemical processes. Ultraviolet radiation from the sun interacts with methane and other trace gases, leading to the production of complex hydrocarbons. Some of these compounds precipitate, forming a thick orange-brown smog that shrouds the surface in an ethereal glow. Visibility is limited, creating an atmosphere that remains elusive and mysterious. Temperature fluctuations also influence this region, with surface temperatures hovering around -180 degrees Celsius. The haze serves as an insulating blanket, maintaining a relatively stable environment. This unique combination of atmospheric conditions has led to the formation of features akin to Earth's geological processes, albeit at a much slower pace. The interplay of temperature, pressure, and chemical reactions underscores the complexity of Titan's atmosphere, a vital component in understanding this distant world. Methane serves a fundamental role in Titan's climate, acting as both a greenhouse gas and an active participant in the Moon's complex atmospheric chemistry. In this frigid environment, it exists in various states, from gaseous clouds to vast lakes and rivers of liquid methane. The presence of these bodies of liquid contributes to a unique cycle, akin to the hydrological cycles observed on Earth, albeit driven by significantly different conditions. Evaporation from the lakes occurs under the influence of solar radiation, transforming liquid into vapor. This vapor subsequently rises, cools, and condenses, leading to the formation of clouds. Precipitation in the form of methane rain falls back to the surface, replenishing the lakes and rivers. This cyclical process fosters a dynamic climate system where surface features continuously reshape in response to the changing atmospheric conditions. The impact of seasonal changes on methane distribution is pronounced. As Titan orbits Saturn, variations in sunlight drive fluctuations in temperature, which in turn influence the behavior of methane. The resulting shifts can lead to the expansion or contraction of liquid bodies, altering the landscape over time. The intricate balance of methane's presence and its interactions with atmospheric components reveals critical insights into Titan's potential for supporting prebiotic chemistry, offering tantalizing clues about the possibilities of life beyond Earth. Discovered in 1690, Titan emerged as Saturn's largest moon, captivating the imagination of astronomers and scientists alike. Initial observations revealed a thick atmosphere, predominantly composed of nitrogen, with a surface obscured by a dense haze. This atmosphere, unique among celestial bodies, hinted at complex chemical processes occurring within its depths. Voyager 1's flyby in 1980 marked a pivotal moment in understanding this distant world. The spacecraft provided the first detailed images of Titan, confirming its status as a significant body within the solar system. The discovery of its dense atmosphere, coupled with the presence of surface features resembling lakes and rivers, ignited scientific curiosity regarding its hydrological processes. Subsequent observations from the Cassini spacecraft, which entered orbit around Saturn in 2004, expanded the knowledge base significantly. Cassini's radar and infrared instruments penetrated the thick haze, revealing vast expanses of liquid methane and ethane. These findings provided direct evidence of a hydrological cycle that parallels Earth's ours, albeit with hydrocarbons instead of water. The implications of these observations extend beyond mere geophysical interest. They suggest a complex climatic system, challenging existing concepts of habitability and fueling ongoing research into the potential for life in environments vastly different from our own. The Cassini-Huygens mission marked a significant turning point in the exploration of Titan. Launched in 1997, the spacecraft embarked on a journey that would reveal unprecedented details about Saturn and its moons. This mission provided a wealth of data, revealing Titan's dense atmosphere, composed primarily of nitrogen, with traces of methane and other organic compounds. These components contribute to the unique hydrocarbon lakes and rivers that dot the landscape. Upon arrival in 2004, Cassini began sending back images that showcased the moon's intriguing surface features. The presence of large liquid methane bodies indicated a hydrological cycle akin to that of Earth, albeit distinct in its composition. The Huygens probe descended through Titan's thick atmosphere in January 2005, landing softly on its surface. This landing provided direct measurements and observations, confirming the presence of a diverse range of organic materials. The mission's findings significantly expanded the understanding of Titan's geology and meteorology. Data indicated that the moon experiences seasonal changes, influencing the distribution of its liquid methane. Features resembling river channels suggested possible erosion processes, while the exploration of the surface chemistry hinted at complex organic reactions. Insights gained from this mission continue to drive questions about the potential for life and the broader implications for astrobiology in the universe. Understanding Titan's surface composition reveals a world shaped by complex interactions between its atmosphere and the myriad of hydrocarbons present. A thick, orange haze blankets this region, obscuring the surface while filtering sunlight. The surface itself is a mix of icy materials and organic compounds, with large expanses of liquid methane and ethane forming lakes and seas. These bodies of liquid exhibit a striking similarity to Earth's water bodies, yet they exist in an environment where temperatures hover around -193 degrees Celsius. The striking contrast between the frozen landscape and the flowing hydrocarbons speaks to the unique geological processes that have shaped Titan over millennia. Organic molecules, created through atmospheric chemistry, likely rain down onto the surface, contributing to a rich tapestry of compounds. The presence of large, dark regions suggests areas where sediments have settled, indicating an active geological history influenced by cryovolcanism. Evidence of dunes formed by wind-blown particles adds to the understanding of Titan's dynamic atmosphere, hinting at atmospheric circulation patterns similar to those found on Earth. These features underscore the complexity of this moon, offering clues about its past and the processes that continue to shape it today. The intricate interplay between solid, liquid, and gaseous states on Titan presents a unique opportunity to study alternative geochemical processes. The formation of methane lakes on Titan is a result of its unique atmospheric and surface conditions. In the frigid environment, where temperatures hover around -193 degrees Celsius, methane exists in a liquid state, filling vast basins scattered across the terrain. These bodies of liquid are not merely random collections. They form through complex geological and meteorological processes that mimic aspects of Earth's hydrological cycle. The surface is shaped by erosion and sedimentation, influenced by rainfall and evaporation cycles. Methane clouds drift through the thick atmosphere, occasionally releasing their contents to create transient lakes. When precipitation occurs, it replenishes these lakes, maintaining their presence. Wind patterns further affect the distribution of methane across the surface, leading to the formation of intricate shorelines and varying lake sizes. In some regions, the lakes appear as deep depressions surrounded by a landscape of icy ridges and organic-rich deposits. Over time, this interplay of environmental factors fosters a diverse array of surface features, revealing insights into Titan's dynamic geological history. Beyond their immediate aesthetic, these lakes offer clues to the moon's potential for harboring prebiotic chemistry, inviting contemplation of the processes that govern such alien worlds. Each lake, then, becomes a focal point for understanding the complexities of this distant moon. Seasonal transitions on Titan introduce intricate cryogenic weather patterns that actively shape its landscape. These fluctuations arise from the moon's elliptical orbit and axial tilt, leading to variations in temperature and atmospheric pressure. During its long, frigid winters, methane condenses into clouds, resulting in precipitation that nourishes the expansive lakes below. This cycle of evaporation and condensation creates a dynamic and ever-changing environment. When summer arrives, temperatures rise slightly, allowing methane to transition from liquid to gas. The evaporation process contributes to a thick haze that envelops the surface, obscuring visibility and altering the coloration of the lakes. This haze acts as a shield, reflecting sunlight and influencing the thermal properties of the moon's surface. Such changes affect the composition of the atmosphere, which is predominantly nitrogen, with trace amounts of methane and other hydrocarbons. Wind patterns, driven by temperature differences, further modify the landscape. These winds can stir the surface of liquid methane, creating ripples and waves that shift the sediment and affect the shoreline. Occasionally, they lead to the formation of dunes composed of hydrocarbon-rich materials, which shift over time. Overall, these seasonal changes contribute to a complex interplay of chemical and physical processes, providing insights into Titan's intriguing climate system. This region features an expansive network of lakes, rivers, and seas, distinguished by their fluid methane composition. The largest body of liquid, known as Kraken Mare, spans an area comparable to the Caspian Sea on Earth, showcasing vast expanses of smooth, reflective surfaces. Surrounding topographies reveal intricate shorelines, where the transition from solid to liquid offers a glimpse into Titan's geological history. Smaller lakes, such as Ontario Lacus, exhibit diverse shapes and sizes, some resembling familiar terrestrial forms while others challenge conventional expectations. River channels meander through the landscape, sculpted by the subtle forces of erosion and liquid flow. Each channel signifies a unique interaction between the atmosphere and surface, suggesting ongoing hydrological cycles that shape this distant world. Cryovolcanism may also influence the geography of Titan, with possible ice volcanoes contributing to the formation of new terrains. These phenomena add layers of complexity, indicating a dynamic environment beneath the icy crust. The distribution of these features points to a remarkable variety of ecosystems that exist within its frigid climates. In examining these lakes, rivers, and seas, the significance of Titan's geography becomes clear. It serves not only as a testament to the Moon's geological processes, but also as a fascinating analog for studying extraterrestrial environments. The unique composition of Titan's surface reveals a striking contrast when juxtaposed with Earth's familiar water bodies. Methane, acting as a primary liquid here, takes on roles that water fulfills on our planet, establishing an intriguing comparison between these two substances. The lower temperature of Titan allows methane to exist as a liquid, a state that enables it to create vast lakes and rivers, shaping the landscape in ways that evoke terrestrial features. Methane's properties differ significantly from those of water. The lower density of liquid methane results in a different buoyancy and flow dynamics. Observations indicate that methane evaporates and condenses in a cycle akin to the hydrological processes on Earth. Yet the underlying mechanisms operate under Titan's frigid conditions. The distinct interaction between methane and the atmospheric pressure creates a unique set of climatic phenomena, such as the formation of clouds composed of methane droplets. While water is essential for life as we know it, the presence of liquid methane opens the door to alternative forms of chemistry and potentially life forms that could thrive in such an environment. The interaction between these substances and the solid subsurface, believed to be composed of water ice, further enriches the geological narrative of this distant moon, inviting a deeper inquiry into the nature of its surface and potential for life. The chemistry of methane on Titan serves as a crucial component in understanding its atmosphere and surface interactions. Predominantly found in both gaseous and liquid forms, methane plays a vital role in shaping the environmental conditions. This hydrocarbon, along with ethane and various other complex organic compounds, contributes to the Moon's distinct atmospheric characteristics. These molecules undergo continual cycling, driven by solar radiation and other environmental influences. Photochemical reactions in the upper atmosphere result in the production of additional hydrocarbons, which eventually precipitate into the lakes and seas below. The presence of these compounds fosters a unique chemical environment distinct from Earth's water-based systems. Temperature fluctuations on Titan create a dynamic landscape where methane can exist in various states. The average surface temperature hovers around 193 degrees Celsius, allowing methane to remain stable as a liquid under its thick atmosphere. In this region, the delicate balance between gaseous and liquid methane shapes not only the topography, but also the potential for prebiotic chemistry. Understanding these processes further illuminates the pathways through which simple molecules may evolve into more complex organic structures. The exploration of Titan's methane-rich environment continues to offer intriguing possibilities for astrobiology, suggesting that the building blocks of life may exist within its frigid expanse. This frigid expanse is also home to unique geological features known as cryovolcanoes, which exhibit the potential for active geological processes. These formations, composed primarily of water ice and other volatiles, contrast sharply with the surrounding landscape of methane lakes. Their presence indicates that beneath Titan's icy crust, a subsurface ocean may exist, providing the necessary heat for cryovolcanic activity. The surface of Titan reveals a striking array of these cryovolcanoes, some towering several kilometers high. Their profiles suggest a history of eruptions, where slushy mixtures of water and ammonia might have erupted into the frigid atmosphere. This activity highlights a dynamic world that is continually reshaping itself. The interplay between liquid methane and icy materials creates a landscape that is both alien and fascinating. Analysis of these geological formations could yield insights into Titan's evolutionary history and its potential for hosting life. The composition of cryovolcanic materials may provide clues about the subsurface ocean's chemistry and its ability to support biological processes. Observations from orbiting spacecraft have captured images that hint at the complexity of this unexplored region. Understanding these features will deepen our comprehension of icy bodies in the outer solar system, revealing the diverse processes that govern their evolution and stability. The subsurface ocean plays a critical role in shaping Titan's environment and influencing its geological activity. Beneath the thick and nitrogen-rich atmosphere lies a vast expanse of liquid water, maintained in a state of partial freezing due to the immense pressures exerted by the overlying layers. This ocean, thought to be a salty brine, interacts with the moon's icy crust, facilitating a complex exchange of materials and energy. Geological features such as cryovolcanoes may arise from this subsurface ocean, propelling slushy mixtures of water and ammonia to the surface. The presence of these volatiles contributes to Titan's unique landscape, marked by a striking contrast between solid ice and liquid methane. The dynamic interplay between the ocean and the overlying materials is instrumental in reshaping the surface, leading to the formation of intricate patterns and depressions. This region exhibits evidence of tectonic processes, with features suggesting that the icy crust may be slowly drifting or deforming. The subsurface ocean thus serves not only as a reservoir of liquid water, but as a driving force behind the moon's geological evolution. Details gleaned from studying these interactions provide insight into the potential for habitability in similar icy worlds beyond our solar system, underscoring the significance of Titan's subsurface ocean in planetary science. Geophysical processes shape the unique landscape of Titan, particularly in the formation of its methane lakes. The surface is marked by vast, shallow basins where liquid methane collects, creating a network of lakes and rivers. These features arise from a combination of climatic and geological forces. Seasonal changes induce a cycle of evaporation and condensation, causing the methane to flow and pool in depressions. The composition of Titan's crust plays a pivotal role as well. Icy materials, primarily water ice, undergo deformation under pressure. This interaction leads to the creation of subsurface reservoirs, which may contribute to the surface lakes through cryovolcanism. These processes suggest a dynamic environment where liquid methane interacts with solid ice, furthering the complexity of Titan's geology. Thermal gradients also influence the behavior of these lakes. Variations in temperature can cause the methane to shift in physical state, enabling the formation of transient features that evolve over time. These subtle changes indicate a responsive system, one that reflects the intricate balance of energy exchange between the surface and atmosphere. Observations reveal that the lakes may also experience evaporation, contributing to atmospheric methane. This cycle underscores the interconnectedness of Titan's surface and its atmosphere, illustrating the dynamic nature of this distant world. The life cycle of methane on Titan reveals a complex interplay between evaporation, condensation, and precipitation. In this region, methane exists in various forms, from gaseous clouds to liquid lakes. These lakes, primarily composed of methane and ethane, exhibit a surface tension unlike that of water, allowing for unique interactions with the atmosphere. Evaporation occurs as sunlight warms the surface, transforming the liquid into vapor. This process feeds into the atmosphere, where methane gas accumulates, contributing to the formation of thick clouds. Once conditions are favorable, these clouds condense, resulting in methane rain. This precipitation replenishes the lakes and rivers below, continuing the cycle. The chemical interactions within this environment are noteworthy. Ultraviolet radiation from the distant sun drives photochemical reactions, breaking down methane molecules and contributing to the formation of more complex organic compounds. These reactions yield a rich array of hydrocarbons that settle on the surface, creating diverse geological features. Methane's presence is further influenced by Titan's seasonal changes. The tilt of its axis leads to variations in sunlight exposure, affecting evaporation rates and precipitation patterns. This cyclical nature of methane dynamics shapes the landscape, with features appearing and disappearing over time, illustrating the ever-evolving character of this enigmatic moon. Surface temperatures on Titan remain consistently frigid, hovering around -295 degrees Fahrenheit. This extreme cold plays a crucial role in the moon's atmospheric and geological processes. The dense atmosphere, primarily composed of nitrogen, contributes to a greenhouse effect, albeit a subdued one. It prevents significant heat from escaping, resulting in local temperature variations that can influence methane distribution and the behavior of its lakes. Repeat, in this region, the interaction between the thick atmosphere and the surface creates unique climatic phenomena. The presence of clouds, primarily composed of methane and ethane, can lead to precipitation events, which may temporarily alter the surface. These clouds can form at higher altitudes, where temperatures are slightly warmer, yet they retain a cold composition that can impact the frigid landscape below. In some areas, topographical features such as mountains and dunes can create microclimates. These variations can result in localized warming, enabling the liquid methane to exhibit different behaviors in adjacent regions. The ebb and flow of these elements contribute to the moon's dynamic surface, leading to the constant reshaping of its features. Studies suggest that such environmental fluctuations may influence the composition of the lakes themselves, highlighting the intricate relationship between temperature and the presence of liquid hydrocarbons, further deepening the intrigue surrounding Titan's unique climate. The interaction of methane and ethane within these lakes reveals a complex chemical landscape. Methane, the primary component, exists alongside ethane, creating a dynamic equilibrium in this frigid environment. The lakes serve as vast reservoirs where these hydrocarbons can mix, leading to the formation of intricate surface patterns and diverse chemical processes. Ethane, while less abundant, plays a crucial role in determining the physical properties of these bodies of liquid. Variations in the concentration of ethane can significantly influence the density and viscosity of the lakes, affecting how methane behaves in the liquid medium. This interaction is further enhanced by the low temperatures, which allow for the stability of these hydrocarbons in a liquid state. The presence of ethane contributes to the unique reflective properties observed on the surface, creating a mesmerizing visual display under Titan's dim sunlight. In addition to their physical characteristics, the interplay between these compounds has implications for potential biological processes. Organic chemistry may be occurring in these lakes, where the reactions of methane and ethane could foster conditions conducive to life. The ongoing exploration of Titan seeks to unveil these mysteries, revealing the processes that shape its lakes and the broader implications for understanding extraterrestrial environments. Each observation adds a layer to the comprehensive understanding of this distant world. Hydrocarbon chemistry plays a pivotal role in unveiling the complexities of Titan's environment. This region is characterized by the presence of vast lakes and rivers, predominantly formed by methane and ethane. These compounds exist in liquid form due to the Moon's frigid temperatures, providing a unique laboratory for studying organic chemistry beyond Earth. The interactions between these hydrocarbons are essential for understanding the potential for prebiotic chemistry, possibly offering insights into the origins of life. The atmosphere, rich in nitrogen, creates a dynamic interplay with surface liquids. These gaseous compounds are subject to photochemical processes, resulting in the formation of complex organic molecules. This transformation contributes to the intriguing possibility of an extraterrestrial chemical factory, where simple molecules evolve into more sophisticated structures. The presence of clouds and precipitation suggests a hydrological cycle, further emphasizing the dynamic nature of this alien landscape. Research indicates that the solid surface may also harbor a variety of organic materials shaped by the continuous erosion and sedimentation processes. This interplay of liquid and solid phases provides an environment ripe for chemical reactions that could mirror those of early Earth. Understanding these processes enables scientists to draw parallels and distinctions between Earth and Titan, enriching the ongoing exploration of planetary science and astrobiology. The methane cycle on Titan operates with striking parallels to Earth's own hydrological processes. Evaporation occurs when sunlight warms the surface, causing methane to transition from liquid to gas. This process is vital for maintaining the planet's atmospheric balance, facilitating the gradual buildup of methane clouds. These clouds, composed of gaseous methane, drift across the landscape, influenced by the Moon's gentle winds. Condensation follows, as cooler temperatures in the upper atmosphere cause this gas to revert into liquid droplets. The resulting methane clouds can be observed forming and dissipating, a phenomenon that illustrates the dynamic nature of Titan's atmosphere. This cycle hinges on the delicate interplay of temperature and pressure, allowing for the efficient transfer of methane from the surface to the atmosphere and back again. Precipitation occurs when conditions are ripe for these droplets to coalesce and fall back to the surface, often resulting in rain-like events of liquid methane. Such precipitation can reshape the terrain, carving intricate channels and forming new lakes. These ephemeral lakes accumulate and drain, contributing to the ever-changing landscape. The entire methane cycle is a cornerstone of Titan's climatic system, revealing the Moon's capacity for complex atmospheric processes. Reminiscent of those found on Earth, but distinct in their chemical makeup and behavior. These intricate methane lakes are deeply influenced by Titan's orbital dynamics, which dictate the Moon's seasonal variations. The elliptical orbit results in significant changes in sunlight exposure, leading to fluctuations in temperature and pressure. This cyclical pattern drives the evaporation and condensation of methane, maintaining a delicate balance that sustains these liquid bodies. During the equinox, sunlight reaches the equator more directly, promoting evaporation. As methane vapor ascends, it contributes to the atmospheric density, affecting cloud formation. The interaction between the atmosphere and surface creates a unique weather system, characterized by the occasional rain of liquid methane. This precipitation replenishes the lakes, ensuring their persistence in the otherwise frigid environment. Polar regions experience contrasting conditions, especially during their extended winters. Here, the colder temperatures cause methane to freeze, transforming liquid into solid, which alters the landscape. The progression of seasons also influences the size and distribution of these lakes, as they ebb and flow in response to Titan's axial tilt and orbital eccentricity. Understanding these dynamics provides insight into the broader implications for Titan's climate. The interplay between orbit and methane lakes not only shapes the surface, but also influences the atmospheric composition, contributing to the Moon's complex and evolving ecosystem. A multispectral approach reveals the intricate features of Titan's lakes, highlighting variations in their chemical and physical properties. These vast bodies of liquid methane and ethane exhibit distinct spectral signatures that provide insights into their depth, composition, and temperature. Observations from various wavelengths allow scientists to detect subtle differences in the surface textures, which may indicate variations in the underlying geology or the presence of solutes. The spectral data collected from Titan's atmosphere and surface also help in understanding how these lakes interact with the surrounding environment. For instance, the absorption characteristics of methane change across different wavelengths, creating a rich dataset that informs models of atmospheric processes. This analysis extends to understanding the seasonal cycles that govern evaporation and precipitation patterns, contributing to the cyclical nature of Titan's methane lakes. As the seasons shift, the lakes themselves may respond, expanding or contracting based on fluctuating temperatures. This dynamic behavior is crucial for predicting future changes in Titan's climate and can shed light on the Moon's potential for hosting prebiotic chemistry. The presence of hydrocarbon rain and its interaction with surface features further complicates this delicate ecosystem. Each observation adds a layer to the understanding of Titan, revealing a world where liquid hydrocarbons dominate and hinting at the potential for chemical processes akin to those found on early Earth. The stability of Titan's lakes is intricately linked to its unique gravitational environment. With a surface gravity approximately 14% that of Earth's, the behavior of liquids here diverges significantly from terrestrial experiences. This reduced gravitational pull allows for the formation of expansive, shallow lakes, where the liquid methane and ethane ripple gently across vast surfaces. Waves can develop, but they remain subdued, influenced by the minimal gravitational force acting upon them. The interplay between this gravity and the surrounding atmospheric pressure contributes to the distinct characteristics of these lakes. The atmosphere, rich in nitrogen, exerts a significant influence, creating a balance that maintains the integrity of these bodies of liquid. Variations in temperature further enhance this stability, as seasonal changes may cause the lakes to expand and contract, yet they retain their liquid form due to the low freezing point of methane. Wind patterns across Titan's surface can also affect lake dynamics, generating currents that may redistribute hydrocarbons and sediments. Such movements are subtle, yet they play a crucial role in shaping the evolving landscape. The presence of these methane lakes, stable under Titan's specific conditions, invites exploration into the myriad of chemical interactions occurring within. This environment may offer clues to the processes that govern planetary bodies beyond our own, revealing the cosmic tapestry of fluid behavior. Patterns of erosion and sedimentation in these methane lakes provide insight into the dynamic processes shaping Titan's surface. The interaction between liquid methane and the icy crust leads to a unique form of erosion distinct from terrestrial experiences. It creates a landscape where delicate features such as rimmed shorelines and intricate channel systems emerge from the gradual sculpting of this frigid environment. As methane flows in and out, it carries fine particles which settle at the lake beds, forming layers. These sediments reflect the varying conditions over time, capturing shifts in climatic patterns and chemical interactions. The layering process reveals a history of liquid dynamics, showcasing how cycles of evaporation and condensation influence the landscape's evolution. The subtle ripples across the surface of the lakes often indicate wind patterns, while larger features suggest the influence of geological activity. The formation of islands and other structures within the lakes speaks to the ongoing interplay between erosion and sediment deposition. Each lake serves as a record, documenting the passage of time and the environmental changes that may have affected this region. This continuous cycle underscores the complexity of Titan's hydrology, inviting further exploration into its role within the broader context of planetary science and the potential for astrobiological implications. Advancements in remote sensing techniques have enabled scientists to probe the depths of Titan's methane lakes with unprecedented accuracy. These innovations, utilizing synthetic aperture radar and altimetry, provide critical data on the physical characteristics of these enigmatic bodies of liquid. The penetration of radar waves allows for the mapping of surface features, revealing subtle variations in elevation that suggest varying depths across different regions. This region has been found to host lakes that vary significantly in size and depth, with some reaching depths of up to 100 meters. Measurements indicate that the shallower areas exhibit a more dynamic surface, influenced by atmospheric conditions, while the deeper sections display a relative calm. The interplay between these depths and the planet's atmospheric pressure contributes to the unique behavior of methane, which exists in a liquid state under Titan's cold conditions. Observations of the surface reflectivity and texture have hinted at the presence of sediment layers, providing insight into the geological history of the region. These findings not only enhance our understanding of Titan's methane lakes, but also inform models of planetary formation and evolution. Each measurement contributes to a growing body of knowledge, illuminating the intricacies of this alien world and its potential for harboring life. Meteorological phenomena on Titan present a unique interplay between wind and liquid methane. Variations in atmospheric pressure create brisk currents that traverse the surface of these expansive lakes. Wind patterns influence not only the surface tension of the liquid, but also the formation of waves, shaping the shoreline dynamics in ways akin to terrestrial environments. These winds, while gentle in comparison to those on Earth, exert a subtle force that stirs the methane, leading to the emergence of ripples and small swells. Such movements can alter the distribution of solutes within the lakes, potentially affecting the chemical interactions that occur beneath the surface. The influence of wind extends beyond the immediate surface, as the agitation can also promote mixing of layers, impacting temperature gradients and stratification. Research indicates that these wind-driven processes can lead to localized weather patterns, generating clouds of ethereal haze above the lakes. These clouds hold important clues regarding the composition of Titan's atmosphere, revealing insights into the interactions between the surface and the vast expanse above. And studying these dynamics, scientists aim to deepen their understanding of Titan's methane lakes, paving the way for future exploration and inquiries into the potential for chemical pathways that may support life or life-like processes in this otherworldly environment. The exploration of Kraken Mare presents a unique opportunity to delve into the largest sea on Titan, spanning over 400,000 square kilometers. It dominates the landscape, offering a vast expanse of liquid methane and ethane. The surface exhibits an intriguing array of features, including large waves and intricate shorelines, shaped by atmospheric conditions and tidal forces. Underneath this liquid layer lies a mystery, with potential interactions between the hydrocarbons and the icy substrate, possibly creating a complex chemical environment. The shoreline reveals a variety of textures and formations, suggesting a history of ebb and flow, erosion, and sediment deposition. These processes play a crucial role in shaping the chemistry of the sea and surrounding regions. Remote sensing instruments have provided critical data, mapping the sea's depths and temperature variations, uncovering potential areas of interest for future missions. The interaction between Titan's dense atmosphere and its surface has implications for understanding not only the Moon's geology, but also the broader dynamics of icy celestial bodies. These findings contribute to a growing comprehension of how such environments function, potentially illuminating pathways for the emergence of prebiotic chemistry. In this remote world, the exploration of Kraken Mare serves as a focal point for researchers and scientists, granting insights that could reshape our understanding of life's potential beyond Earth. The role of Titan's topography plays a crucial part in the distribution of its lakes, shaping the landscape of this alien world. Variations in elevation and surface features dictate where these vast bodies of liquid methane can form and persist. Large basins, created by ancient impacts or tectonic shifts, often serve as natural reservoirs, allowing for the accumulation of hydrocarbon lakes. Accumulation of hydrocarbon lakes. Some regions exhibit a remarkable interplay between low-lying areas and elevated terrains, where the gradient influences fluid movement. The interaction between atmospheric pressure and the chemical composition of the surface further complicates these dynamics. This region showcases a landscape marked by intricate channels and valleys, creating pathways through which liquids can flow, carve, and eventually settle. Satellite imagery provides valuable data, revealing clusters of lakes that appear interconnected, suggesting an intricate hydrological cycle. The varying depths and sizes of these lakes indicate diverse histories, influenced by both geological processes and climatic conditions over time. Evidence of seasonal changes in lake levels hints at a dynamic environment where evaporation and precipitation cycles could play a role in maintaining the balance of this system. The interplay of topography and hydrocarbon distribution not only informs scientists about Titan's current state, but also prompts inquiries into the Moon's geological past, revealing the mechanisms that have shaped its surface over millions of years. Understanding Titan's climate patterns involves sophisticated modeling techniques that simulate its atmospheric processes. These models account for the dense atmosphere, primarily composed of nitrogen, with a significant presence of methane and trace gases. By recreating the interactions between these components, researchers can predict how changes in temperature and pressure influence cloud formation and precipitation patterns. Seasonal variations reveal insights into Titan's climate, showcasing a cycle where methane may condense into clouds, leading to rainfall that replenishes the lakes and rivers. Observations suggest that this cycle mirrors those found on Earth, albeit with unique characteristics due to Titan's frigid temperatures and different chemical makeup. Models also explore the influence of sunlight on methane's behavior, indicating that solar radiation drives some of the atmospheric dynamics. It plays a crucial role in the complex interaction between surface and atmosphere, affecting methane's stability and distribution. Continued advancements in simulation technology allow for increasingly detailed representations, enabling scientists to predict future climatic events. With each iteration, a clearer understanding of this moon emerges, revealing a world shaped by processes that, while alien, share fundamental similarities with terrestrial phenomena. Insights gained from these models enhance comprehension of both Titan's climate and broader planetary science, opening avenues for exploration beyond our own world. The organic compounds present in this region play a pivotal role in shaping Titan's unique ecosystem. Comprising primarily hydrocarbons and complex organic molecules, these substances contribute to the Moon's intriguing chemical processes. They exist in various states, creating a dynamic interplay with the atmosphere and surface, influencing everything from weather patterns to potential biochemistry. These compounds interact with Titan's thick atmosphere, consisting mainly of nitrogen, punctuated by methane and hydrogen. Sunlight causes photochemical reactions, leading to the production of more complex molecules, which accumulate in the lakes and seas. This process suggests an active environment, one where organic chemistry flourishes under conditions vastly different from those on Earth. The presence of liquid methane and ethane on Titan's surface serves as a solvent for these organic compounds, much like water does on Earth. This similarity raises questions about the potential for life, as these compounds may provide the necessary building blocks for biological processes. Although the frigid temperatures render Earth-like life forms unlikely, alternative forms of life could potentially emerge in such an environment. Understanding these organic systems is crucial for unraveling the mysteries of Titan's past, including its geological history and climatic evolution. The study of these compounds offers valuable insights into the fundamental processes that govern not only Titan, but also celestial bodies throughout the universe. The presence of hydrocarbon lakes raises intriguing questions regarding the potential for life. Conditions on Titan, with its frigid temperatures and diverse chemical makeup, create a unique environment. Liquid methane and ethane, abundant on its surface, present an alternative to water as a solvent for biochemical reactions. This prospect broadens the scope of astrobiological possibilities, challenging traditional notions of habitability. These environments may harbor complex organic molecules, essential building blocks for life. The interactions between methane, ethane, and other compounds could lead to prebiotic chemistry, akin to the processes theorized to have occurred on early Earth. The thick atmosphere, rich in nitrogen and organic haze, provides a shield against harmful radiation, creating a stable environment conducive to chemical evolution. The examination of potential microbial life in these lakes could reshape understanding of life's resilience. Extremophiles on Earth thrive in harsh conditions, suggesting that similar adaptations might exist elsewhere. The exploration of Titan serves as a critical step in assessing the likelihood of extraterrestrial life, expanding the search beyond traditional aqueous environments. In-depth analysis of Titan's surface and atmospheric chemistry will contribute to the ongoing discourse about life's prevalence in the universe. This inquiry into the Moon's unique conditions exemplifies the merging of planetary science and astrobiology, revealing the intricate connections between chemistry and the potential for life beyond Earth. Methane plays a pivotal role in prebiotic chemistry, serving as an essential building block for organic compounds. On Titan, the abundant presence of methane in its lakes and atmosphere creates a unique environment for the synthesis of complex molecules. These gaseous and liquid forms interact with ultraviolet radiation from the distant sun, fostering a variety of chemical reactions that may mirror the early processes on Earth. With this region, the cold temperatures allow methane to remain in liquid form, creating vast seas that are unlike any found on our planet. The interaction between methane and other elements, such as nitrogen and hydrogen, leads to a diverse chemistry that could produce amino acids and other vital precursors necessary for the emergence of life. The atmospheric dynamics further contribute to this process, with seasonal cycles of evaporation and condensation influencing the distribution of these compounds. Through this perspective, the methane lakes of Titan serve not only as intriguing geological features, but also as potential laboratories for studying origins of life. The processes occurring within these liquid expanses may offer insights into how similar conditions might foster life elsewhere in the cosmos. As research continues to unfold, the importance of methane in understanding prebiotic chemistry remains a cornerstone in the quest to unravel the mysteries of life's beginnings. The dynamics of Titan's atmosphere and surface interaction reveal a complex interplay of processes that shape this enigmatic moon. Dense clouds of nitrogen and methane envelop the surface, creating a unique atmospheric pressure about 1.5 times greater than that of Earth. This thick atmosphere supports the formation of clouds, which occasionally release liquid methane, contributing to the extensive lakes and rivers scattered across the landscape. Surface temperatures hover around -193 degrees Celsius, allowing methane to exist in a liquid state, unlike on Earth, where it typically remains gaseous. These frigid conditions foster a cycle of evaporation and precipitation, akin to hydrological cycles on our planet. Methane lakes serve not only as a defining feature, but also as potential sites for prebiotic reactions. The interaction between the surface and the atmosphere influences the chemical composition of the lakes, which may reflect complex organic processes. Winds sculpt the surface, eroding features and redistributing materials, while cryovolcanism occasionally introduces fresh methane reservoirs. As sunlight filters through the hazy atmosphere, it instigates photochemical reactions, potentially forging intricate organic compounds. These compounds, along with the unique climatic and geological phenomena present, contribute to a fascinating environment that continues to intrigue scientists exploring the possibility of extraterrestrial life. Technological advancements have become essential for studying Titan's methane lakes, allowing researchers to delve into the complexities of this alien world. Unmanned aerial vehicles equipped with spectrometers can traverse the thick atmosphere, capturing high-resolution images and analyzing the chemical composition of the surface below. These devices operate under extreme conditions, with temperatures plummeting to -180 degrees Celsius. Rovers designed for icy terrains are also deployed, capable of navigating the diverse landscapes of Titan. Their instruments measure the viscosity and density of methane lakes, providing insight into the behavior of these unusual liquids. Advanced sonar systems map the underwater topography, revealing features that may hint at geological processes similar to those found on Earth. Communication technologies relay critical data back to mission control, allowing scientists to monitor environmental changes in real time. These innovations facilitate a deeper understanding of how atmospheres and liquids interact in alien settings. Laboratory simulations on Earth mimic Titan's frigid conditions, supporting the development of hypotheses regarding organic chemistry in such environments. The combination of aerial, surface, and laboratory technologies forms a comprehensive approach to exploring Titan's lakes. This multifaceted strategy not only enriches our knowledge of the Moon but also enhances the broader pursuit of life beyond our planet. The future of exploration on Titan is poised to unveil even deeper insights into its complex environment. Proposed missions aim to expand our understanding of the Moon's methane lakes and their potential for harboring unique forms of life. One noteworthy endeavor includes a lander specifically designed to navigate the dense atmosphere and touch down on the surface, where it will analyze the chemical composition of liquid methane and ethane. These missions are not limited to landers alone. Concepts for aerial drones are also under consideration, capable of soaring through the thick clouds, conducting aerial surveys, and capturing high-resolution images of Titan's varied landscapes. This approach allows for the examination of regions that are otherwise inaccessible, revealing the intricate interactions between the atmosphere and the surface. On the surface, the advanced instruments on board these proposed missions are expected to measure atmospheric pressure, temperature, and wind patterns, providing insights into seasonal changes and weather phenomena unique to this distant world. These data will be crucial in understanding the Moon's climate and the role it plays within the broader context of the Saturnian system. Each proposed mission represents a step toward not just understanding Titan, but also refining our search for life in the cosmos. As technology progresses, the potential for discovery grows, marking an exciting chapter in humanity's exploration of the outer solar system. Titan's magnetic field plays a crucial role in shaping its atmospheric chemistry. This region, enveloped in thick orange haze, reveals unique interactions between charged particles and the Moon's dense atmosphere. As solar winds collide with this magnetic field, they create a complex environment where ions and neutral particles engage in intricate processes. These interactions contribute to the formation of atmospheric compounds that are not found elsewhere in the solar system. The magnetosphere acts as a shield, protecting Titan from direct solar radiation while allowing certain particles to penetrate, initiating chemical reactions. Methane, abundant in the atmosphere, undergoes photolysis, breaking down under the influence of ultraviolet light from the sun. This process results in the creation of complex organic molecules, contributing to the Moon's enigmatic haze and potentially supporting prebiotic chemistry. As these reactions unfold, they feed back into Titan's surface environments. The methane lakes and rivers serve as both reservoirs and catalysts for further chemical processes. This interconnectivity underlines the importance of Titan's magnetic field in maintaining its atmospheric balance and influencing surface dynamics. The stability offered by the magnetic environment allows for sustained chemical cycles, creating an atmosphere rich in organic compounds. Understanding this relationship enhances the comprehension of Titan's potential habitability and its role within the broader context of astrobiological research. Ultraviolet radiation plays a significant role in the surface processes of Titan, influencing its atmospheric chemistry and the interaction of various compounds. This radiation penetrates the thick atmosphere, instigating complex photochemical reactions that transform simple molecules into more complex organic compounds. These processes contribute to the formation of haze particles, which gradually descend and coat the surface, creating a dynamic interplay between the atmosphere and the ground below. The presence of methane in lakes and rivers, juxtaposed with the organic haze, highlights the unique environment. Ultraviolet light, while penetrating the atmosphere, also facilitates the breakdown of methane, leading to the production of ethane and other hydrocarbons. This transformation is critical, as it hints at the potential for diverse chemical pathways, analogous to those observed in prebiotic conditions on Earth. Surface observations reveal that the interaction of ultraviolet radiation with the nitrogen-rich atmosphere can lead to the generation of complex organic molecules. These molecules may play a pivotal role in the environment of Titan, fostering conditions that mimic certain aspects of Earth's early biosphere. The ongoing reactions, intensified by this radiation, contribute to the ever-evolving landscape. Through the study of these processes, a clearer picture emerges of Titan's intricate environment, emphasizing the importance of ultraviolet radiation in shaping its surface and atmospheric dynamics. Evidence points to a rich geological history, where liquid methane and ethane play a crucial role in sculpting the terrain. This region exhibits features reminiscent of river deltas, formed as hydrocarbons flow and accumulate, creating intricate patterns that suggest a dynamic past. These deposits indicate significant seasonal changes as the precipitation of methane rain alters the surface, leading to erosion and sediment transport. The presence of vast lakes and seas suggests that Titan has undergone periods of intense geological activity, marked by the subsurface movements of various materials. Cryovolcanism, characterized by the eruption of icy mixtures, may have reshaped its crust, introducing new compounds and altering existing structures. These phenomena indicate that Titan is not a static world. Rather, it is a planet of constant change, influenced by both internal processes and external forces. Surface features, such as mountains and valleys, provide insight into this geological evolution. Some elevations exhibit signs of erosion, hinting at a history of weathering by liquid hydrocarbons. The interplay between the atmosphere and surface melts away the rigid boundaries traditionally associated with celestial bodies. Geological mapping reveals a patchwork of ages, with some regions appearing younger than others, suggesting varying periods of activity and dormancy. Understanding this complexity aids in piecing together Titan's past, revealing a world that continues to challenge our perceptions of planetary evolution. Rodanthe Guataril region plays a significant role in the formation and distribution of hydrocarbon lakes. This area, characterized by its unique climate and geological features, showcases an abundance of methane and ethane, essential components of these liquid bodies. Elevated temperatures in this belt allow for the stability of these hydrocarbons in liquid form, unlike at the colder poles, where solid and gaseous states prevail. In this region, the interaction between surface features and atmospheric conditions creates dynamic environments. Wind patterns contribute to the shaping of the lakes, influencing their size and distribution. The presence of vast, smooth expanses indicates areas where liquid has pooled, while the surrounding rugged terrains suggest tectonic activity that has influenced the landscape over millennia. Chemical processes also play a crucial role in the maintenance of these lakes. Photolysis, driven by sunlight, breaks down atmospheric methane, leading to complex hydrocarbons that can seep into the lakes. This ongoing interaction highlights a delicate balance between evaporation and replenishment, ensuring that these lakes maintain their existence. The equatorial region serves not only as a geochemical laboratory, but also as an indicator of Titan's climatic shifts. Each lake stands as a testament to the intricate interplay of Titan's geology and atmospheric phenomena, providing insights into the Moon's ongoing evolution. Understanding the seasonal cycle of methane lakes reveals a complex relationship between Titan's atmospheric conditions and surface processes. These bodies of liquid methane undergo significant fluctuations influenced by the Moon's tilt and orbit. Seasonal changes initiate variations in temperature, leading to the evaporation and condensation of methane. The cycle orchestrates a rhythm of liquid movement, where methane can transform from liquid to gas and back again, driven by the subtle shifts in Titan's climate. The presence of clouds composed of methane and ethane indicates periods of precipitation sown, mirroring terrestrial weather patterns. During these times, the lakes swell, capturing the falling rain and altering their dimensions. The interplay of evaporation and condensation contributes to the formation of expansive brine deposits, shaping the landscape over time. visible in the polar regions. These changes further emphasize the impact of Titan's axial tilt, creating a dynamic landscape where the lakes may expand or recede with the seasons. Observations suggest that these cycles could last several Earth years, a pace dictated by Titan's longer orbital period. These phenomena not only enhance the understanding of Titan's climate, but also invite questions about the potential for prebiotic chemistry within these methane-rich environments. The lakes may offer a glimpse into the Moon's complex ecosystem, holding secrets yet to be uncovered. The effects of Titan's orbit on lake morphology are significant and multifaceted. This Moon's unique elliptical orbit leads to variations in tidal forces, influencing the distribution and depth of the liquid methane and ethane that populate its surface. These forces can cause the lakes to expand and contract, altering their shapes and sizes over time. Such fluctuations provide insights into the dynamic processes occurring underneath the surface. Lakes situated in regions with varying orbital characteristics exhibit distinct features. Shallow basins may develop pronounced shorelines, shaped by the constant ebb and flow of liquid hydrocarbons. In contrast, deeper lakes experience relative stability, maintaining a more uniform depth, while fostering unique sedimentary processes. These processes are vital for understanding the chemistry present within Titan's atmosphere and surface. Surface winds, generated partly by Titan's rotation, also play a role in lake dynamics. Wind patterns can lead to the formation of waves, contributing to erosion along the edges and impacting the sediment distribution. This interaction between atmospheric conditions and liquid bodies is essential in shaping the overall landscape. Shaping the overall landscape. Insight into the Moon's orbital mechanics provides context for these phenomena. Understanding how these tidal and wind-driven forces interact with Titan's lakes enhances comprehension of the geological and chemical processes in this alien environment. The study of these lakes continues to reveal the complexities of Titan's atmospheric and surface interactions. Icebergs, composed of water, ice, and other frozen materials, drift within the expansive methane seas of Titan. The presence of these frozen formations provides insight into the Moon's unique geological processes. They form as a result of the interplay between the cold temperatures and the abundant liquid methane, which acts as a solvent in this frigid environment. These icebergs vary in size and shape, with some reaching several meters in height. Their surfaces display intricate textures, shaped by the constant movement of the liquid below. As they float through the dense atmosphere, changes in pressure and temperature can lead to the sublimation of the ice, resulting in transient features that constantly reshape the landscape. Analysis of the compositions of these icebergs reveals a complex mixture of water ice, organic compounds, and possibly other materials. This mixture suggests potential chemical processes occurring beneath the surface, hinting at the dynamic nature of Titan's environment. The movement of these icebergs is influenced by the currents and tides within the methane seas, driven by Titan's gravitational interaction with Saturn. Tracking their paths can provide valuable information about the underlying topography and the overall hydrological cycle of this distant world. Each observation contributes to a deeper understanding of Titan's atmospheric dynamics and its potential for hosting complex chemical processes. The interplay between solar radiation and the methane that dominates Titan's atmosphere reveals a complex chemical landscape. Methane photolysis occurs as ultraviolet light from the sun penetrates the thick, hazy atmosphere, breaking down methane molecules into simpler hydrocarbons such as ethane and diacetylene. This process not only alters the composition of the atmosphere, but also influences the formation of organic compounds, which may play a crucial role in prebiotic chemistry. Within this dense haze, The resulting products from methane degradation descend into the surface, contributing to the enigmatic lakes and seas. These hydrocarbons, alongside other atmospheric constituents, generate a rich environment conducive to various chemical reactions. The interactions between these molecules promote a cycle of creation and transformation, establishing a unique chemical equilibrium. Temperature variations across this region further influence these processes. As the dynamic climate leads to fluctuations in methane concentration and the rates at which reactions occur, the presence of seasonal changes may also alter the distribution of these compounds, impacting their spatial and temporal availability. Understanding these chemical dynamics provides insight into Titan's potential for harboring complex organic chemistry, which may resemble processes thought to have occurred on early Earth. The intricate balance of these reactions continues to be a subject of active research, revealing the profound mysteries of this distant moon's atmosphere. The possibility of subsurface life on Titan has captured the interest of scientists. Beneath the thick layers of ice that cover its surface, a hidden ocean may exist, composed primarily of water. This region, shielded from the harsh conditions above, could provide a stable environment for microbial life forms to thrive. Measurements from radar and infrared observations hint at the presence of liquid water beneath the icy crust, suggesting a dynamic interaction between the surface and its subsurface. The intriguing presence of organic compounds and the potential for hydrothermal activity present an environment rich in the elements essential for biological processes. This hypothesis raises questions about the adaptability of life forms that might exist in such an alien ecosystem, potentially utilizing methane or ethane as solvents instead of water. Exploratory missions aimed at Titan seek to gather more data, focusing on the composition of its ice and the dynamics of its subsurface ocean. Understanding the interactions between the icy surface and the watery depths could shed light on the moon's potential to host life. Each discovery adds a layer of complexity to the understanding of this enigmatic world, offering insights into life's resilience and adaptability beyond Earth. The quest for knowledge continues, revealing the boundless possibilities within this remote celestial body. The ethane lakes on Titan present a fascinating contrast to their methane counterparts, underlining the diversity of this extraterrestrial environment. Both bodies of liquid exist in a state dictated by the frigid temperatures of the moon, yet they exhibit unique characteristics that warrant examination. Ethane, being a byproduct of methane's chemical processes, forms its own distinct pools, contributing to the complexity of Titan's hydrological cycle. The ethane lakes, while less abundant than the methane lakes, cover considerable areas across the surface. They reflect the dim light of the distant sun, creating a shimmering effect that is both ethereal and otherworldly. These bodies of liquid differ not only in composition but also in their physical properties. Ethane possesses a lower density than methane, resulting in varying buoyancy effects and influencing the interactions with the surrounding atmosphere. The presence of ethane suggests ongoing geological processes, perhaps indicating recent activity beneath the icy crust. These lakes may serve as indicators of Titan's dynamic nature, challenging existing models of planetary formation and evolution. The interplay between the two types of lakes fosters a deeper understanding of Titan's climate and atmospheric interactions. This celestial body continues to intrigue scientists, each discovery revealing further intricacies within its liquid landscapes and gaseous envelope. Investigating the lakebed morphology provides insights into the processes shaping this unique environment. The smooth, Reflective surfaces of these methane lakes often conceal complex features beneath. Sonar mapping techniques reveal varying depths, with some depressions reaching nearly 100 meters, while others hold shallower pools that may host intricate sediment structures. The lakebeds may exhibit patterns reminiscent of terrestrial river deltas and coastal features, suggesting a history of erosion and sediment transport driven by the Moon's atmospheric dynamics. These formations indicate that cryovolcanism and tectonic activity likely contribute to the evolution of the landscape. The presence of organic compounds within the sediments suggests a rich chemical repertoire, possibly similar to early Earth environments. Analysis of the lakebed material indicates varying compositions, with some areas rich in hydrocarbons and others displaying a more diverse assortment of organic molecules. This chemical diversity may provide clues to potential prebiotic processes. In addition to physical features, the thermal dynamics of the lakebeds also warrant examination. Their interaction with the surrounding atmosphere and subsurface layers can influence methane evaporation and condensation cycles. This interplay is essential for understanding Titan's climate system and the broader implications for astrobiology beyond our own planet. Each study conducted contributes to a deeper comprehension of this remarkable world. This Uiumbatal synchronous rotation on Titan's climate is profound. This phenomenon results in one side of the Moon perpetually facing Saturn, while the opposing side remains in darkness. The temperature differences between these regions create distinct atmospheric conditions. On the sunlit side, solar energy warms the surface, leading to evaporation of methane into the atmosphere. This process generates clouds, which are primarily composed of methane and nitrogen, contributing to a unique weather system. Athernings, on the dark side, the lack of direct sunlight leads to frigid temperatures, allowing methane to condense back into liquid form. These contrasting environments contribute to a dynamic climate where methane rains may occur, particularly during seasonal changes. The gradual evolution of Titan's atmosphere reveals intricate patterns influenced by the gravitational interactions with Saturn. The Moon's thick haze provides insulation, maintaining a delicate balance between heat retention and loss. These features suggest a climate system that is both stable and variable, with the potential for periodic changes driven by seasonal shifts. Understanding this climate system enhances knowledge not only of Titan, but also provides insights into similar celestial bodies within our solar system. Such studies pave the way for future explorations, seeking to uncover the complexities of extraterrestrial atmospheres and their implications for potential habitability. Titan presents a unique opportunity for exoplanetary studies, serving as a model for understanding atmospheres beyond Earth. Its dense atmosphere, primarily composed of nitrogen with methane clouds, acts as a laboratory for scientists examining similar conditions on distant worlds. The chemical processes occurring in its atmosphere mirror those hypothesized on exoplanets that orbit other stars, particularly those within the habitable zone. This region's surface features, including vast lakes of liquid methane and ethane, provide insight into cryovolcanism and surface erosion processes that may be present on icy bodies throughout the cosmos. Observations indicate the presence of organic compounds, suggesting a complex interplay of chemistry that could inform searches for life in environments vastly different from our own. The interaction between the atmosphere and surface liquid plays a crucial role in defining Titan's climate system, offering critical parallels for exoplanets with substantial atmospheres. The exploration of such features fosters a deeper understanding of atmospheric dynamics, cloud formation, and precipitation mechanisms, These insights not only enhance comprehension of Titan itself, but also serve as a foundational reference for interpreting data from exoplanetary atmospheres. As missions continue to gather data, the comparisons drawn from Titan will refine methodologies used in the quest to identify potentially habitable exoplanets across the universe. The role of these methane lakes extends beyond mere intrigue. They serve as a vital component in Titan's climate regulation. The liquid methane, in its various states, interacts with the atmosphere in a manner akin to water on Earth. Evaporation from these surfaces contributes to the formation of clouds, which are thus formase. Surface temperatures hover around -180 degrees Celsius, creating conditions where methane and ethane exist in a liquid state. The chemical reactions occurring within these lakes can gradually alter the atmospheric composition, affecting both temperature and pressure. The presence of these hydrocarbons promotes a unique greenhouse effect, enabling the Moon to retain heat despite its distance from the Sun. Wind patterns across this region shape the lake's surfaces, leading to the formation of waves and ripples. These movements can further enhance mixing within the liquid layers, promoting a dynamic equilibrium essential for maintaining the delicate balance of Titan's meteorological phenomena. The interconnectedness of these lakes with the atmosphere illustrates the complexity of Titan's environmental processes, offering insight into similar systems that may exist on other celestial bodies. Observations from future missions will undoubtedly deepen understanding of these intricate interactions. The relationship between Titan's lakes and atmospheric pressure is a defining characteristic of this enigmatic moon. Methane, existing as both a gas and a liquid, plays a pivotal role in the dynamics of the atmosphere. At temperatures around -180 degrees Celsius, the atmospheric pressure is approximately 1.5 times that of Earth, allowing methane to remain stable in liquid form. This pressure, combined with the unique conditions present, leads to the formation of extensive hydrocarbon lakes and seas. For these bodies of liquid not only reflect the surrounding landscape, but also influence local weather patterns. Evaporation from the lakes contributes to the formation of clouds and possibly precipitation, creating a cyclical interaction between the surface and the atmosphere. The pressure-driven equilibrium facilitates the maintenance of liquid methane and ethane, which shape the Moon's surface through erosion and deposition processes, all sur-terre or non-deposition processes. Understanding this delicate balance provides insights into Titan's climatic systems and the potential for cryovolcanic activity beneath the surface. The lakes serve as indicators of subsurface processes, revealing how they may connect to the atmosphere above. Variations in atmospheric pressure can lead to fluctuations in lake levels, offering clues about Titan's geological and meteorological history. Each observation adds depth to the ongoing exploration of this unique world, highlighting its complex interplay of elements. The spectroscopic analysis reveals a myriad of compounds present in Titan's methane lakes. Infrared spectroscopy provides essential insights into the chemical composition of these liquid bodies. Specific absorption features indicate the presence of ethane, diacetylene, and other hydrocarbons, each contributing to the lake's intriguing characteristics. These compounds, derived from the breakdown of methane under ultraviolet radiation, suggest a dynamic chemical environment where reactions occur continuously. A detailed examination of spectral data showcases varying concentrations of these substances across different regions. Some areas exhibit higher ethane levels, potentially due to evaporation processes, while others are enriched with heavier hydrocarbons, reflecting a complex cycle of liquid precipitation and evaporation. This chemical diversity hints at a rich prebiotic environment where organic molecules may play a crucial role. Temperature variations influence the lake's surface dynamics, affecting the solubility of various compounds. In colder regions, the thickness of liquid layers may increase, impacting the overall composition observed through spectroscopic methods. The existence of solid methane and ethane hydrates in these areas further complicates the chemical landscape. Understanding this chemistry is essential for grasping Titan's potential for harboring life or prebiotic chemistry. The exploration of these lakes through spectroscopic means continues to unveil the secrets of this distant world, offering a glimpse into its unique and evolving environment. Liquid methane and ethane exist in a stable state across Titan's surface, contrasting starkly with the familiar behavior of liquids on Earth. The frigid conditions, with temperatures averaging around 193 degrees Celsius below zero, create an environment where hydrocarbons remain in liquid form. This stability results from the unique atmospheric pressure, slightly higher than that of Earth, which allows these compounds to defy expectations. The lakes themselves are vast, some spanning hundreds of kilometers, and present a serene yet enigmatic landscape. Their surfaces occasionally ripple, disturbed by winds or other atmospheric phenomena. The properties of these liquids differ markedly from their terrestrial counterparts. The low temperatures lead to a density that affects their interaction with Titan's solid surface, allowing for the formation of intricate shorelines and unique geological features. Observations reveal a complex interplay between the atmosphere and these lakes, with evaporation and precipitation cycles that mirror, in some respects, the water cycle on Earth. This phenomenon highlights the intricate balance that sustains liquid stability in such an alien environment. The existence of these methane lakes raises questions about the potential for chemical processes similar to those that led to life on Earth, inviting further inquiry into the possibilities of life in such extreme conditions. Surface mobility on Titan reveals intriguing characteristics. Observations indicate that liquid hydrocarbons are not merely stagnant, they exhibit dynamic flows across the landscape. These flows carve intricate networks of channels, suggesting a form of geomorphological activity driven by climatic conditions unique to this moon. Seasonal changes on Titan lead to variations in the distribution of these lakes and rivers, hinting at a fluid system governed by the interplay of surface temperature and atmospheric pressure. The composition of these hydrocarbons is primarily methane and ethane, which behave differently than water. Their lower density and distinct properties allow for unique flow patterns, creating terrains that resemble river deltas and floodplains. This region showcases how liquid hydrocarbons can shape the surface, similar to how water does on Earth, albeit under vastly different temperature and pressure conditions. The presence of wind further contributes to this mobility. It stirs the surface, creating ripples and waves across the lakes, and facilitating the movement of methane vapor into the atmosphere. Such interactions between the atmosphere and liquid surface layers are crucial for understanding this moon's climate system. Studying these hydrocarbon flows provides insights into the geological history of Titan, revealing the processes that have sculpted its surface over millions of years, and deepening the understanding of its complex environment. Seasonal changes significantly influence lake interaction on Titan, altering both the surface and atmospheric conditions. The duration of Titan's seasons spans approximately 30 Earth years, causing dramatic shifts in temperature and atmospheric pressure. These variations lead to a cyclical pattern of evaporation and precipitation of methane, which in turn affects the size and distribution of these liquid bodies. During the warmer periods, sunlight reaches the surface more intensely, promoting evaporation from the lakes. This process enriches the atmosphere with methane, contributing to the formation of clouds, which eventually precipitate back into the lakes. Conversely, as temperatures drop, condensation occurs, leading to the accumulation of methane on the surface once more. The interplay of these processes creates a dynamic system where lakes can expand and contract, reflecting the changing seasons. By flexibility seeks the formation of features such as shorelines and ice rafts. Driven by the interplay between the liquid methane and the colder atmospheric temperatures, such phenomena offer insights into the climatic evolution of Titan, as well as the potential for chemical reactions occurring in its lakes. Continued observation of these seasonal interactions is essential for revealing the intricacies of Titan's climate and its broader implications for understanding planetary systems beyond our own. The impact of cosmic radiation on Titan's methane cycle is profound, influencing both the stability and distribution of this vital resource. Cosmic rays, high-energy particles originating from beyond the solar system, interact with Titan's atmosphere, generating complex chemical reactions. This process leads to the production of various hydrocarbons, which play a crucial role in the Moon's atmospheric composition. The energetic particles penetrate the thick haze, initiating reactions that transform methane into heavier organic compounds. These transformations contribute to a dynamic balance within Titan's atmosphere, where methane is continuously produced, consumed, and reformed. The interplay between cosmic radiation and methane dynamics sheds light on the Moon's potential for sustaining prebiotic chemistry. In the upper atmosphere, the breakdown of methane by cosmic radiation forms a variety of byproducts, which can eventually fall to the surface. This precipitation of organic material contributes to the unique landscape, characterized by lakes and rivers of liquid methane and ethane. The constant cycling of these hydrocarbons, influenced by external cosmic forces, reveals the complexity of Titan's environment. Studying these interactions not only enhances comprehension of Titan's atmospheric processes, but also offers insights into the potential habitability of other celestial bodies. Such knowledge expands the boundaries of astrobiology, bridging the gaps in our understanding of life beyond Earth. Titan's enigmatic environment presents intriguing possibilities for future human exploration, particularly in the realm of resource utilization. The presence of vast methane lakes and ethereal clouds of nitrogen suggests an abundance of materials that could support prolonged human presence. This region's atmospheric density is approximately 1.5 times that of Earth, offering a unique advantage for human activities, including potential flight. Exploration missions to Titan would necessitate advanced technology for atmospheric entry and surface navigation. Robotic probes have already shown that the surface features a diverse array of landscapes, including dunes and icy crusts. This variety indicates not only geological activity, but also points to the potential for discovering novel chemical processes that could be harnessed for future endeavors. The stable conditions and relatively mild temperatures make Titan an ideal candidate for the establishment of research outposts. These facilities could serve as platforms for scientific inquiry, as well as testing grounds for life support technologies essential for human missions further into the solar system. The availability of liquid methane could also serve as a fuel source for return missions to Earth or deeper space exploration. Thus, Titan's rich and complex environment stands as a promising frontier, offering vital insights into our solar system and the potential for humanity's next great journey beyond Earth. The potential for exploration is accompanied by significant challenges. Titan's liquid surface, composed primarily of methane and ethane, presents unique landing difficulties. The density of these hydrocarbons is greater than water, which complicates buoyancy and landing dynamics. Any descent vehicle must account for this factor, requiring specialized designs to ensure stability upon contact. The thick atmosphere, primarily nitrogen, further complicates the landing process, With its high pressure and low temperatures, this region demands advanced thermal protection systems to withstand the harsh conditions. Wind patterns and potential storms can create unpredictable currents, posing risks during descent and landing. Surface exploration is hindered by an opaque haze that enshrouds Titan, obscuring visibility. This thick atmosphere limits the effectiveness of optical navigation systems, necessitating the development of alternative guidance technologies. Radar, sonar, and other remote sensing methods might provide crucial data for safe landings. Once on the surface, the presence of large hydrocarbon lakes could complicate mobility. The unique terrain, featuring both solid and liquid regions, requires adaptable landers capable of traversing diverse environments. Understanding the composition and behavior of these liquids is essential for assessing long-term exploration viability. These challenges highlight the intricacy of Titan's environment, necessitating innovative solutions to unlock its mysteries. The advancement of radar technology plays a pivotal role in understanding Titan's hydrocarbon bodies. This remote sensing method allows scientists to penetrate thick atmospheric layers, revealing the hidden landscapes beneath. Utilizing synthetic aperture radar, it captures high-resolution images of liquid methane and ethane lakes, providing crucial data on their size, shape, and distribution. Mapping these bodies unveils their dynamic nature, showcasing fluctuations in surface levels and changes in shoreline configurations. Such observations indicate the influence of Titan's atmospheric conditions on its surface, where seasonal variations may lead to the filling or draining of these lakes. This interaction between the atmosphere and surface liquids is a key area of study, as it reflects broader climatic patterns and geological processes. The radar's ability to identify the reflective properties of hydrocarbons enables researchers to discern between solid and liquid surfaces, enhancing the understanding of Titan's complex geology. Areas previously obscured by clouds are now accessible for analysis, contributing to a more comprehensive view of this moon's environment. The implications of these findings extend beyond mere observation. They inform models of Titan's hydrological cycle, suggesting the potential for active weather systems similar to those on Earth. This reinforces the Moon's status as a significant site for ongoing exploration and scientific inquiry. The interplay of Titan's lakes and atmospheric dynamics reveals a complex system that shapes its environment. These expansive bodies of liquid methane serve not only as reservoirs but also as active participants in the Moon's weather patterns. Evaporation from these lakes contributes to the formation of clouds, which in turn play a crucial role in precipitation cycles. The continuous exchange between liquid and vapor sustains a unique hydrological cycle distinct from that of Earth. The surface temperatures hover around -190 degrees Celsius, allowing methane to exist in liquid form. This cold environment constrains the energy processes, resulting in a serene yet intricate balance. Winds sweep across the surface, causing ripples and waves on the lakes. These movements disturb the liquid, releasing methane into the atmosphere, where it can accumulate and eventually condense, leading to ethereal rains. The presence of organic compounds further enriches this atmosphere, offering clues to potential prebiotic chemistry. The interaction between the lakes and the atmosphere creates a landscape that is both alien and familiar. The vast, reflective surfaces contrast sharply with the hazy orange skies, embodying the dual nature of this moon. Atmospheric pressure, significantly higher than that of Earth, adds another layer of complexity, influencing the behavior of these lakes and the dynamics of Titan's environment. The polar regions of Titan present a unique interplay between the atmosphere and the expansive methane lakes. Seasonal shifts in sunlight exposure lead to variations in temperature, which, in turn, affect the state of the liquid methane. During the long, frigid winter months, these bodies of liquid gas may partially freeze, transforming the surface into a crust of solid methane. As the seasons transition, the return of sunlight raises temperatures, prompting the reactivation of liquid flows and reshaping the landscape. Within Baith of Duinwes, this region experiences a distinct climatic pattern characterized by the movement of ethereal clouds composed of methane and nitrogen. These clouds condense and precipitate, providing a source of replenishment for the lakes. The interactions between the atmosphere and the polar lakes lead to complex hydrological cycles, contributing to the overall climate dynamics of this moon. In addition, the presence of large, interconnected lakes creates microclimates that further influence local weather patterns. The evaporation of methane contributes to cloud formation, while the lakes themselves act as thermal reservoirs, moderating temperature fluctuations. This delicate balance of processes helps sustain the unique ecosystem present in these polar areas. On a broader scale, Titan's polar regions serve as a laboratory for understanding the implications of liquid methane on planetary atmospheres, offering insights that extend beyond its own boundaries. The geological history of Titan reveals a complex narrative shaped by interactions between its atmosphere and surface. Lake studies offer critical insights into this history, elucidating the processes that have sculpted its landscape over eons. These vast bodies of liquid methane, along with ethane and other hydrocarbons, act as both eroding agents and transport mechanisms, carving channels and creating intricate shorelines. Sediment analysis from these lakes indicates a dynamic environment where deposition and erosion occur in tandem. The layering found within the sedimentary deposits suggests cyclical climatic changes, perhaps influenced by seasonal variations in sunlight and thermal activity. This cyclical nature hints at a richer climatic history, one where periods of stability alternated with more volatile phases. Geological formations surrounding these lakes provide further context, revealing ancient valleys and plains that once may have harbored different compounds, potentially including water in its liquid state. The shifting composition of the atmosphere over time appears to have played a significant role in the evolution of these features. Through careful examination of these formations and the lakes themselves, scientists can reconstruct Titan's past and draw parallels to other celestial bodies. The findings contribute not only to understanding Titan's geological narrative, but also to the broader discourse on planetary evolution and atmospheric processes throughout the cosmos. These methane lakes embody a unique aspect of Titan's environment, showcasing an interplay between geology and the atmosphere. Covering vast expanses, they are the largest bodies of liquid on this moon, composed primarily of methane and ethane. The existence of this liquid is a result of Titan's frigid temperatures, which allow hydrocarbons to remain in a liquid state despite their gaseous nature elsewhere in the solar system. Surface features surrounding these lakes reveal a dynamic landscape shaped by both erosion and sedimentation processes. The presence of waves and ripples indicates wind activity, while varying depths suggest a complex interaction between the moon's surface and atmospheric conditions. This interplay provides critical insight into the hydrological cycle present on Titan, illustrating how liquid methane can replicate certain processes observed in Earth's water cycle. The lakes not only serve as geological markers, but also as potential sites for prebiotic chemistry. The interaction between liquid methane and the organic compounds found on Titan could yield insights into the origins of life. These conditions foster an environment that, while inhospitable by terrestrial standards, could harbor unique biochemical processes. Studying Titan's methane lakes thus deepens the understanding of extraterrestrial environments, prompting reflections on the potential for life beyond Earth and the diverse evolutionary pathways that may exist across the universe. Theoretical models of Titan's surface and subsurface processes reveal a complex interplay between its atmosphere, liquid hydrocarbons, and icy crust. This region functions as a dynamic system where ethereal clouds release methane rain, replenishing the lakes and rivers below. The presence of these liquids suggests that erosion and sedimentation shape the landscape, creating intricate shorelines. The subsurface processes are equally intriguing. Below the icy shell, a possible ocean of water and ammonia may exist, communicating with the surface through geological features such as cryovolcanoes. These formations are hypothesized to erupt, releasing subsurface fluids into the frigid environment above. Such interactions may not only alter the surface topography, but also influence the chemical composition of the lakes. The seasonal cycles experienced on Titan further complicate the models. With a lengthy rotation period of about 16 Earth days, variations in sunlight impact methane evaporation and condensation, leading to the formation of transient features across its surface. These phenomena provide insight into the Moon's climate and its potential for sustaining complex chemical reactions. Understanding these processes contributes to a broader comprehension of planetary bodies in the outer solar system. The insights gained from Titan's unique environment may offer clues about the dynamics of other celestial bodies, expanding the scope of astrobiological research and our quest for life beyond Earth. Interdisciplinary approaches to Titan research are paving the way for deeper understanding of its complex system. Scientists from various fields are collaborating, integrating planetary science, atmospheric chemistry, and astrobiology to decode the mysteries held within this enigmatic moon. This collaboration is essential as the interaction between Titan's thick atmosphere and its surface lakes creates a dynamic environment that requires multifaceted analysis. Models of methane hydrology are being developed to simulate the movement of liquid methane across the surface. These simulations help to predict seasonal changes, revealing how precipitation and evaporation cycles operate in Titan's frigid climate. The study of organics, produced through photochemical processes in the upper atmosphere, is particularly vital, as these compounds could provide insights into prebiotic chemistry. Instruments aboard future missions are being designed to probe Titan's surface and subsurface, utilizing radar and spectrometry to study its geological features and potential cryovolcanism. Understanding these processes will shed light on the Moon's evolutionary history, informing theories about the development of habitable environments elsewhere in the solar system. The integration of robotic exploration with laboratory-based research enhances the potential for groundbreaking discoveries as interdisciplinary teams work towards a comprehensive understanding of Titan. They expand the horizons of planetary exploration and the search for life beyond our own world. Research into Titan's unique environment reveals intriguing possibilities for future colonization. It possesses a dense atmosphere, rich in nitrogen, creating conditions that are markedly different from Earth, yet surprisingly stable for exploration. Surface temperatures hover around -193 degrees Celsius, presenting a challenge for human habitation, but also a potential advantage, as these frigid conditions may preserve organic compounds. Hydrocarbon lakes, primarily composed of methane and ethane, offer a glimpse into alternative energy sources. These bodies of liquid gas could be harnessed to support initial human outposts. The presence of complex organic molecules suggests that, while hostile, it may also be an environment rich in resources that could be utilized for survival. The thick atmosphere provides shielding from radiation, which is a significant benefit when considering long-term habitation. This protective layer could allow for the construction of habitats that, through careful engineering, could sustain human life. Importantly, the absence of a breathable atmosphere encourages the design of closed-loop life support systems. Assessing the viability of Titan for colonization also involves evaluating the technological advancements required to explore and inhabit such a distant world. Innovations in propulsion, habitat construction, and life support systems are crucial to ensuring success in this endeavor. Each finding contributes to a greater understanding of the challenges and opportunities that lie ahead in humanity's quest to extend its reach into the cosmos. A multitude of narratives has emerged from the exploration of Titan and its unique environment. This celestial body has inspired countless works of science fiction, where its methane lakes and dense atmosphere serve as a canvas for imaginative storytelling. Writers have envisioned colonies thriving on its surface, depicting human adaptation to extreme conditions. These portrayals reflect not only the fascination with the moon's alien landscapes, but also a deeper contemplation of humanity's potential in the universe. The allure of Titan lies in its otherworldly characteristics. With a surface covered in liquid methane and ethane, it evokes both wonder and curiosity. This region has been depicted as a frontier for exploration, where the challenges of survival are met with ingenuity. These narratives often explore themes of isolation and resilience, mirroring humanity's own journey through the cosmos. In artistic expressions, Titan's atmospheric haze creates a sense of mystery, further enriching the cultural landscape. Cinematic interpretations bring to life the visual splendor of its shrouded surface, inviting audiences to ponder the possibilities of life beyond Earth. The scientific intrigue surrounding its potential for prebiotic chemistry fuels the imagination, leading to speculations about the existence of life forms adapted to such an environment. Such cultural manifestations not only reflect our aspirations, but also underscore the fundamental questions of existence, identity, and exploration that resonate through the ages. This region of Titan, cloaked in a dense atmosphere rich in nitrogen, presents a unique landscape where methane and ethane exist as stable liquids, forming vast lakes and rivers. The presence of these hydrocarbon bodies raises profound questions about planetary processes and the potential for chemistry that diverges from earthly norms. In the context of the solar system, these lakes serve as a reminder of the diverse environments that exist beyond our planet. While Earth is defined by its water, Titan showcases the versatility of hydrocarbons as solvents in its own right. These methane lakes, particularly in the polar regions, exhibit intricate shorelines shaped by erosion and evaporation. The interplay between the cold temperatures and atmospheric pressure allows for the formation of clouds and precipitation cycles that echo the hydrological processes found on Earth, yet operate under vastly different physical conditions. Observations reveal that these liquid expanses may harbor complex organic chemistry, potentially offering insights into the building blocks of life. In this distant world, the surface is dotted with features reminiscent of fluvial systems, suggesting a dynamic interaction between the atmosphere and the surface. Each observation deepens our understanding of not only Titan's geology, but also the broader implications for habitability elsewhere in the cosmos. The presence of these expansive methane lakes raises significant questions regarding the formation and evolution of gas giants. It suggests that similar processes may occur on other celestial bodies, hinting at a commonality in the development of atmospheres across the solar system. This region's unique chemistry, dominated by hydrocarbons, provides a contrasting perspective to the water-rich environments typically associated with life as understood on Earth. These lakes indicate that liquid methane and ethane can exist in stable forms at low temperatures, which may influence the atmospheric dynamics of gas giants. Understanding this behavior contributes to models predicting weather patterns on such planets, illuminating the interactions between their myriad atmospheric constituents. The complex interactions between gas and liquid phases may result in meteorological phenomena distinct from those observed on terrestrial worlds. Fluctuations in surface levels and the formation of clouds over these lakes offer a glimpse into potential weather systems, further expanding knowledge of planetary atmospheres. The possibility of similar bodies elsewhere, especially in the outer planets, suggests that the potential for varied atmospheric compositions and chemical processes exists widely. This realization fosters a broader perspective on habitability, emphasizing that life may not require water as an essential solvent, but rather could adapt to alternative environments shaped by unique chemical frameworks. Titan's role in the search for extraterrestrial life is profoundly significant. The presence of vast methane lakes and seas, combined with a thick atmosphere rich in organic compounds, presents an intriguing landscape for astrobiological exploration. These conditions create a unique environment where prebiotic chemistry could potentially thrive, differing from the water-based life forms found on Earth. The atmospheric pressure at Titan's surface is approximately 1.5 times greater than that of Earth, influencing the behavior of its liquid methane and ethane. This dense atmosphere harbors complex chemistry that may lead to the synthesis of prebiotic molecules. Researchers speculate that these conditions may allow for the emergence of life forms that utilize methane in ways analogous to how earthly organisms utilize water. Surfaces covered in hydrocarbon lakes indicate a dynamic hydrological cycle, albeit one that differs significantly from the traditional water cycle. Instead of rain, methane clouds precipitate liquid methane, replenishing the lakes and creating a continuous system of chemical interaction. This cycle, alongside the presence of potential subsurface oceans, suggests that Titan could harbor environments that support life, albeit in forms vastly different from terrestrial organisms. Observations from missions such as Cassini and the Huygens lander have provided valuable data, further igniting curiosity about the potential for life beyond our planet. The exploration of Titan presents a complex landscape of ethical considerations. The significance of understanding this moon's unique environment is underscored by its potential to expand knowledge of life's possibilities in the universe. The pristine methane lakes and their intricate ecosystems raise questions about the responsibilities inherent in scientific inquiry. The potential for contamination during exploratory missions looms large, highlighting the need for protocols that mitigate human impact on such an untouched world. Regulatory frameworks must evolve to support responsible exploration while balancing the pursuit of knowledge with the preservation of Titan's natural state. The possibility of encountering unknown forms of life introduces further ethical dilemmas. Engaging with environments that may host life forms, even if radically different from those on Earth, demands a cautious approach to prevent unintended consequences of exploration efforts. The role of international cooperation in this endeavor is paramount. Collaborative efforts can foster shared guidelines and best practices, ensuring that exploration is conducted with respect and foresight. As missions are planned, discourse surrounding the ethical implications will shape the future of planetary exploration. These considerations highlight a broader responsibility towards not just understanding other worlds, but also safeguarding their integrity for future generations. This delicate balance between discovery and conservation remains pivotal as humanity ventures into the cosmos. The vast expanses of Titan's surface reveal a landscape sculpted by liquid methane and ethane, unlike anything found on Earth. These lakes, shimmering under a distant sun, stretch across the horizon, their depths concealing the secrets of this moon's atmospheric dynamics. The presence of these hydrocarbons suggests a complex interaction between geological processes and climatic conditions. Analysis of the liquid bodies indicates a potential for chemical reactions that could provide insights into prebiotic chemistry. The striking contrast between the frigid environment and the organic richness invites further investigation. Researchers ponder the implications for astrobiology, contemplating whether life could emerge in such an alien setting. These lakes also pose challenges for exploration. The dense atmosphere obscures visibility, requiring innovative technology to navigate this terrain. Robotic missions could illuminate the processes that have shaped this unique world, mapping the lakes and analyzing their composition in fine detail. The exploration of Titan serves as a reminder of humanity's quest for knowledge and the ethical responsibility that accompanies it. Each mission carries the weight of understanding and preserving these phenomena, ensuring that the exploration of such environments does not compromise their integrity. This world of liquid gas stands as a testament to the complexities of planetary science, inviting a deeper appreciation for the universe's myriad forms and possibilities.